Hey, Cooper, Braden, Ella, Michaela, good to see you here. It is the start of office hours. I was doing all these changes. I put the wrong name in for the office hours. I was like, oh, I gotta change this, gotta change this. Like, oh, everyone's here. Let's do it. How's everyone doing? What questions are there? I've got my cup of coffee. It's almost done. What questions are? Good to see you, Alexander. How you doing? We've got Mubot awake. Let's give out some points. Already see. It's so weird. Could we do the catalog sales company question on the quiz 13? That's so weird. It's like I see the questions on Mubot first. You bet. Let's do the catalog. I feel a bit under weather. Oh no, Alexander. I feel a bit tired too. We're gonna do the catalog sales question, and we need those positive vibes. I need those positive vibes too. Alexander, you help me out too. All about those positive vibes. I slept like over 7 hours last night, but I still feel tired. Maybe just the plan of infinite coffee finally wears down. But I don't know, you ever have that? You like get a full night of sleep and you still feel tired? You're like, I slept. I thought decently, and you're like, I still feel a little tired. It's probably, Reddit is so good about keeping us oh no. Okay, me here to flex the points or flex the sleep. It's the rain for me. Rain will do it too. Oversleeping happens. It is, well, I don't think 7 hours. Task 4, you got it, Ryan. We will do that next year. Cooper, you got this. Well, I don't think I overslept. Like 7.5 hours I got maybe last night, which is, I think you're supposed to get 8, right? Tell me if I'm wrong about this 8 hours of sleep a night. That's what I was told as a kid. And if I was told that as a kid, that has to be the truth, right? Let's go over here. Let's head to the main screen. We're going to do some 320 also. Texas is going well. Hey, Michaela. Yeah, Michaela, you took it last semester, right? No, my points went away. Yes, I love it. Michaela's like, oh, I'm sorry, Michaela. Let's fix Michaela's points right here. We're going to fix Michaela's points, so we're going to do this question. Make sure. Okay, let's fix Michaela's points. I change the points every semester, Michaela, so that way we can reset the points. Let me fix Michaela's points. And Michaela, we also added in that, oh, Michaela, go ahead and check your points, Michaela. Let's turn on the counter. We got the counter on. We got the points on. And we've got, let's do a few 201 questions here. I just wanted to ask, so I'm signing up for BS 474 and BS 475 with you over summer and wanted to know what do you think of about the workload. Brayden, great question right there. I can't even speak this morning. And wow, everyone's here. So good to see everybody. We'll talk about that first, and then we're going to do the 320 questions. Michaela, that is insane. And your tier will go up. We fixed your Bucks right there. So I'm also signed up for Intro to Political Science in case you think it'd be a lot to take. 3 courses is a lot, but here's the really good news. And so I probably will send that because this question's come up a lot. So I'm going to address this, and then we'll do some 201. Don't worry, we'll be doing that in 2-3 minutes here. Depends on your body. So much information, and really just so glad to see everyone here. So here we go with BAS 474. That's I don't even know what the 700 level is. Data mining. Coding in R, and understanding statistical concepts. So the biggest thing about these 2 courses is there's going to be a lot of coding in R. This is time series. And we're going to do coding in R. And there's going to be a big project. A end of semester project. Now, what's really exciting about this with both these courses is if you're taking both of them, you're going to practice all the coding in R. And so I do think taking them both can be very beneficial at the same time, like taking them in the summer. So amazing. Hope to see you. Yeah, of course, Michaela, anytime. Yeah, swing by anytime we're live, say hey, and you've got the points back, but I'll always reset them between semesters. So watch out. You'll lose the points again. Just be like, hey, Brian, and then be like, throw me some points. I'm a previous student. I'll be like, yes. But so I think you're lessening your workload. It's going to be more work, Braden, of course. Like it's 2 courses. 2 courses are, of course, more work than 1 course. But with the coding in R, you're going to get lots of practice. Like sometimes it's hard for people if they take 320, then they take a break, they take 474, they take a break, then they take 475. Like after a break, you kind of like have this like lowering of your skills. It's like learning how to play piano for 6 months and then not playing for 2 years. I got to get a piano. And then playing piano again and then taking a break and then playing piano again. You learn it quicker each time, but with the breaks, your skills kind of drop off. So I think depends, Braden. And here's the big deciding factor, which if you're working, if you're not working, are you going to have a job during the summer? If you don't have a job, I think three is possible. If you have a job, or if you have responsibilities like family or just any sort of responsibilities that would take a large portion of your time. So, yeah, and definitely if you want to take both next semester, I think I heard there may be a sports analytics class. Yeah, we're working towards that. I'd love to be part of that. Yes, a part-time internship. Yeah, I'd be a little more worried, especially with 3 courses. Just depends on the how part-time it is. Like, are we talking like a few hours a week? Are we talking like 20, 30 hours a week? It just depends on how busy you are. I think 2 courses in a summer semester is equivalent to a full load during a regular semester. So 2 courses in the summer, like 2 courses, and it does depend, like, are we talking a film class? Nothing against a film class, but I took a film class and it was a lot easier. I took one of those in the summer. Or are we talking like an upper level mathematics course? I mean, upper level mathematics course, I could probably spend all summer, every waking hour working on it and not do it. Yeah, it just depends on your time management. You will be very busy, I am sure, if you take 2 or 3 courses. But yeah, I mean, if you're like, hey, I'm just gonna buckle down and I'm gonna but be careful. I've learned my lessons about I'm gonna buckle down and work for 6 months. You should sleep, you should eat, you should exercise. Try to keep your life in balance, or your body will scream and say, "What are you doing?" I found that out the hard way. Anyways, enough about me. Let's head over to these questions. But yeah, if you have more questions, let me know. I think they're both great courses, and I think taking them together can really help. You're basically, you have this much work, but if you take them both together, you lower the workload for one, because you're getting your coding skills all together at the same time. So I think it can help to take both. No, Alexander, no. You tell your body, nope. Let's do, there was 2 320 courses. So 2 320 courses. Yeah, awesome. Yeah, no, I really hope you're in class. I want to give students good advice. I want students to take my class, but I want to make sure, everyone has a balanced life too. Which ones did people want? No, I miss my students. But yeah, could we do the catalog sales question? Ella, if you remind me, which one's the catalog sales question? How does it start out? Is it, Ella, is this one, can we do number 3 problem? Yeah, let's do that. And the other part 13 here, we're going to start with Ella's one, and then, oh no, Brian's made 8 errors. What? Mubot. How dare you, Mubot? Let's do Ella's question here, and then we'll go back and we'll do the school referendum. So let's go, and I think there was another one. This is from the next assignment, a catalog sales company. Yes. Okay. Ooh, this one is tricky. This is a multiple choice that continues for forever. So let's do this one right here. I do remember it now. Okay. So they give us confidence intervals right here. And when you get confidence intervals, you need to know that a confidence interval is going to have a center and a margin of error. So the best thing to do when you get this question is to take the interval itself, and we are trying to figure out the true proportion of orders that arrive on time. So when you look at this question, here's your interval. And the interval, if we create it, goes from 79, and you can already see it right there, to 91. And we are trying to figure out the true proportion of orders that arrive on time. So, not this one? Not this one? Okay. There might be another version of it. This one. Is it this one right here, Ella? I think this one's the one that has the multiple parts to it. They do 2 catalog questions. So this one right here is a wording question on figuring out the previous one. Let's just here, we'll do it. You ready? With this previous one right here, I am 95% confident that the true proportion of orders that arrive on time is contained in the interval 79 to 91%. So we got that one done. And then it's the stating if the conclusion is correct or not. Yep. Here we go on catalog question 2.0. So this is very similar, but they're going to give you a bunch of wording that just doesn't work. So when we go right here, let's take the question again. And once again, we are asking about the true proportion of orders that arrive on time. and we have here the interval. The interval is going to be from here to here, which is going to be from 72 to 90%. Now, when we do this, we need to remember the way we write it. We write out I am blank percent confident that the true is contained in the interval blank to blank. We are trying to figure out the true proportion of orders that arrive on time. This is the parameter of interest. And I think people often, just think about this. If you are polling for an election, you're going to take a sample of so many people, and maybe you find out that the candidate has support from the sample of 45%. And we might say we have a margin of error of 5%. So how would you interpret this? So if you're 201, especially, or Ella, or anybody in the chat, I want you to take a moment. Remember, we're pulling for a candidate. I want you to interpret this interval right here for a candidate who's running for election. I am, and we'll say 95% confident, although as though we made a 95% confidence interval. We can put the interval here, but people usually have trouble with the second section of this. I am 95% confident that the true what? Remember, we asked people, are you going to vote for this candidate? So what are we trying to estimate here? Well, we found out in a sample that 45% of people are going to vote for the person. That's the center of the interval. This here is p hat, and this is the margin of error. The margin of error is z times p hat q hat over n square root. And so all of this is the margin of error. Z gives us the confidence level relative to a 95% confidence interval. So we can put a little star on that. Put a little purple star. I am 95% confident the true proportion of people who will vote for the candidates. Ella, you just want everyone another 100 points. That is perfect answer right there. A lot of times when we have written tests, we have to write this out, and that the true proportion of people are like, it's going to, yeah, exactly. Look at Charlie, just all-star in here. Charlie, good to see you. And so the true proportion of people who will vote for the candidate, because that's what we're trying to estimate. So let's look at these answers and see where they're wrong here. And let's just keep saying that, like, I am 90-something, 95% confident that the true proportion of packages that will arrive on time is contained in the interval blank to blank. Between 72 to 90% of packages will arrive on time. Instantaneously, something is wrong right here. It doesn't even give a confidence level. It implies certainty that does not give a confidence level. So this, we didn't even say I am blank percent confident. So no, not happening. That's not statistical. 95% of all the random samples of customers will show 81% of orders arrive on time. Are we, he is Python coded. I didn't code him though. He is Python coded. And if you're good at Python and you want to make stuff from Ubot, hey, this is chapter 13, part 2 homework, part 2. But yeah, Charlie, he is Python coded, and I started to look into recoding him, and he said, no. He said, you're not smart enough. And I said, I'm sorry, I'm Ubot. He said,
I am Ubot.
That's all he said. 95% of all random sample customers will show that 81% of the orders arrive on time. We're not trying to figure out the random samples. So this is just not correct. Much less than 95% will show exactly 81%. So this one's just weird because this is what we saw for the sample customers, but if we repeated it, who knows what we would see with random sample customers? Like, I don't know. This is not about random sample customers. We're trying to estimate the true proportion. That's what our interval does. I'll be making that, Luke, you bet. We've been doing some during office hours, but tomorrow I'm going to start putting them in playlists. If you're in my section especially, stay tuned for a playlist to be sent out to you. A lot of people use Python. Some people use R. It just depends. Check out the business analytics interview we did, and people were like Python R, and it's the war forever. One can be 95% confident that the true population proportion of orders that arrive within 3 days is contained in the interval. This might be correct. We do have the interval correctly made. This statement is not correct because the confidence level must be equal to the mark. No, that doesn't even make sense. This statement is not correct. The interval estimates the population proportion. Wait. No, that looks correct. I mean, this is a correct statement because the interval does estimate the population proportion, but it says that. One can be 95% confident that the true population proportion of orders that arrive within 3 days is between the interval blank to blank. I am 95% confident that the true proportion of packages that arrive within 3 days is contained in the interval blank to blank. Yeah, that looks very correct. One is 95% sure, 95% confident, that between 72 to 90% of the orders placed by the sample customers arise within the time. Now, this is where we need this equation right here, because in my equation right here, what is the sample, like, just tell me numerically, what is the sample proportion? In my equation right here, what is the sample proportion? Hint, it's highlighted. So in my equation right here, what was the sample proportion from the sample I took? What was the sample proportion in this thing I took right here? And you can see the confidence interval. The sample proportion is the center of the confidence interval, as it's shown right there. So you can see in this version I wrote right here that we know the sample proportion. Exactly, the sample proportion is 45. So in this, what is the sample proportion? What is the sample proportion from this? Because we use that to make the interval. So what was the sample proportion for this equation right here? For this one, what was the sample proportion? Since we just did it for that one, we're like, well, we know what it is because we use that to build the interval. So what is the sample proportion for this one? The sample proportion for this one, just like in the previous example, because here it's 45, and here, that's the sample proportion right there. So we know the answer. We know what the sample proportion is. So we don't use the interval to estimate the sample proportion. We know it's 81% because we have data from the sample. So yeah, we know in the sample, we know what percent arrived on time. On 95% of the days, we're not talking about the days. We're talking about like packages individually. The days would be like, this would be a whole different equation. I'm even trying to think how we would do it. We're not talking about days here. We're talking about the true proportion. So the interval is about the parameter, not the days. We're not talking about individual days. We're talking about I am 95% confident the true proportion of packages that arrive on time within 3 days is contained in the interval 72 to 90%. Should get them all correct. We got it. Yeah, let's do this. Does that help out, Ella? I think there was another one people wanted from chapter 13. We'll do some more chapter 13 here, and then we'll hop over to 320 here in a moment. But what was the other ones from chapter 13 people wanted? I know there's the school referendum. We'll do that here in a moment. We've done the first two package problems. Philanthropic organization. What was the other? Was there another chapter 13 part 2? And then I'll do another chapter 13 part 1. And just so good to see everybody. We had so many people come by. I was like, whoa, we got a bunch of people here. Let's see. Catalog sales company. We did that one. And I think there was another one. Need like a referendum on school budget. And we'll do that next. It might be different. It was the other homework. Hey, Michael, good to see you here. Which one, Lizzie, did you want? Go ahead and put in again in the chat which one you wanted. We have the other one from the referendum. So can we do the number 3? Is it number 3 from homework, Lizzie? We can do that one next. So we'll hop over there and do that one. 320 lurker, Nico. That's awesome. We're going to do some 320 in a moment. Can you explain the less than 10% rule? I understand that you have to do it. I just don't know why. So there's a really good article on it. Here, we'll talk about that as we switch over to the homework question. The referendum one? Yeah, let's do the referendum one. That might be your number 3. So the less than 10% rule deals with, this is like the in-depth part of it, deals with finite populations and the way when we take too large of a sample, we actually create a larger error on how we estimate it. And they've shown this to be mathematically. And I used to have a really good article on it. Can I find it? 10%. If anyone finds this, there was an article that had a table that showed the error. And I thought it was the most fascinating article. Fascinating. And I will never find that article again. I will never, ever see that article. I should have saved it. I haven't seen it for years now. And, oh, know, man. I wish they'd show it. I'm going over all these 10% condition articles right here, and the problem is that it creates more and more error in our calculations due to finite populations. Oh, someone's got a Reddit post on it. I just really want to see that table again, because that table made it make perfect sense on the amount of error we get as we increase the proportion of the population we sample. Yeah, and I'll never see that table again. I cannot find it. I don't know why that person who had that awesome website took it down. It was probably too helpful. And I'm just finding a bunch of like tests and stuff that people have posted. So if you happen to find that, I'll try to look for it again, but it disappeared a while back. The referendum, yep, let's do it. Let's do the referendum one. Here we are, the referendum one. I'll disappear for a second. So Jacob, that's a great question. I want to find that table again and I'll show you, but what happens is your error starts to increase exponentially when you oversample finite populations. So as long as that's a little bit of the theory, we can show it mathematically, and they can show mathematical theory behind why sampling more than 10% is bad. It just deals with the equations we use, and they're not properly set up to handle oversampling populations. Like they create more error, and they're just not good equations at some point. So we actually have advanced statistical techniques like permutations, 320, to handle things like that. If we have time after every question, could we do how many random subcategories? Yeah, which one's that on? Again, Ella, tell me which one that's on, and let's take a screenshot of this, and let's do it. We're going to do as many questions as we can today. Let's do it. Okay, we're going to head over here. And here we are. Just before a referendum on a school budget, a local newspaper polls 355 voters to predict whether the budget will pass. So I need help. I need help, everybody. I need you to identify this, and we want to see predicting leading to defeat. This right here. So which things? You got it, Ella. Let's do that one next. We're gonna focus on 320, 201, then we'll focus on 320. So what do we have right here? We need to identify all of these things, and that's the hard one to identify. You are right, and technically it's lowercase n. Technically it's lowercase for sample size. Large n we either use for population size or for I can't even think, for normal curve. Normal curve or population size has a dual purpose. Correct, and everyone's right that this is the population proportion, and the left one is the confusing one, because this is actually suggesting that we observe a p hat less than 50%. So let's look at this right here, because that's where people usually get stuck, and they're like, well, what am I looking for? We are seeing that in a sample, which is a key word for this right here, we're seeing that in a sample, we see a proportion, or that they would predict defeat. So in a sample, they would observe something that would predict defeat, and if this school budget's going to be pulled for, then if they see a sample saying less than 50% would vote for it, they'd say, well, we're going to say that it would be predicted to be defeated. If we were to take a sample of 2 people, just imagine I go out and speak to 2 people. Be very careful. Be very careful. This is where usually we see the mistake. What percent of these people, on average, would you expect to see vote for the budget? If you take a sample of 2 people, what percent, like on average in a sample of, let's say, 2 people, what percent would you expect to see vote for the budget? If you took a sample of 2 people, what percent on average would you expect to see vote for a budget? Given that this is the truth. Exactly. And you're like, wait a minute, but that can't happen. But in the long run, if you took samples of 2 people, like on average, this is saying on average, not in one sample of 2 people, but in the long run, on average, you would see this. Like if you repeatedly took samples of 2 people and you started averaging up like how often they voted for it, you would see this right here on average. Now that also violates a condition, but this is where people are usually like, well, wait a minute. How would you see this? And it's like saying, I take a sample where one person votes for it and the other one doesn't. And then in the other sample, both people vote for it. And then the other sample, both people don't vote for it. You just would see this if you start averaging together sample proportions. So this is the average of a bunch of sample proportions. And we're not taking a sample of 2 right here. We are taking a sample of 355. So we would get a curve like this. And at the center of this curve is going to be 0.53. Now, we do have the mean of this curve, but every curve needs a mean and a standard deviation. And the standard deviation of this curve is going to be p times q over n square root. And that is going to be equal to 0.53. And in chat right now, show them how to get q right here. How do we get q? How do we get q? These are things we should know instantaneously. We just practice it till we're like, oh yes, they are complements of each other. So if p is 0.53, exactly, Lizzie, great job right there. If p is 0.53, then q is 0.47. So you just take the complement and you go here and you go, calculators looking all crazy. P times q over n square root. There we go, 0.026 right there. Here we go. Can I move this all? Ooh, can I? Ooh, wow. It's magic. You know. There we go. And so 0.026, just a rounded version of it. And then we would go down here and start writing out these numbers. We can give a guesstimate of this. We always like to guess the answer. It's a little bit of fun. Can we get it today? Can we get it? So if you notice, the answer here is going to be a little bit below what? So here's where 50% would be at. The answer here is going to be a little bit below what? My brain is breaking. The answer here is going to be a little bit below what? Let's see if the chat sees what I see. So you should see something. Oh, we could just do that. Sure, it's enough information. Enough information to figure out what's going on right here. We know that p hat is going to be... That is enough information on the curve to see that this is going to be a little bit below. Well, it's not going to be at 0.504. It's going to be at 0.50, which is getting... Because we're trying to figure out the probability it would lead to defeat, which is this area right here. And 0.504 is where? 0.504 is one standard deviation below the mean. So we're a little bit below one standard deviation. So people always wonder how I'm guessing these things. They say, well, how do you guess this, Brian? Why do you like to guess it? And I'm like, because it's fun. And so we get two guesses here. This is a harder one to guess. I say that, and then let's see if we get it right. Oh. Yeah, it's going to... I should have done this. Oh, we didn't get it. A little bit below 16. Exactly. Ella, great job. That's what I'm doing right there. Let's go ahead and take the actual numbers, and we're going to go to the David M. Lane applet. So here's the David M. Lane applet. And so with the David M. Lane applet, here it is on the screen in the chat. Let's put in the mean of this and the standard deviation of this. And now we need to go below 50%. Is it closer to that? So it's 12.8 or 12.9 when you round up. So we were close-ish. Really hoping to get one of these. So it was 12.9. So that was the answer right there. And now we got it. So we were just taking a guess, but our picture can give us an idea. And that's kind of one of the important things with this problem is like at least being able to draw it out. And I do want to point out one thing right here. We can z-score this to see if this is unusual. And this would not be that unusual. We can see that the z-score is between -1 and -2. The z-score is just going to be observation minus mean over standard deviation. And we do have the mean and the standard deviation here right now. There's the standard deviation. And here's the mean. The mean of the curve is at the center. And the standard deviation is just the distance going down each one time. So when you do observation minus mean over standard deviation, you're going to go right here and do observation of p hat minus p over the p times q over n square root. And this will give you the z-score. So the z-score is going to be equal to 0.50, which is the observation, minus 0.53 over 0.026. And so we can solve this right now. Let's go ahead and take that. 0.50 minus 0.53 divided by, and the z-score is -1.13, and that's where we should about see that right there. So we can see that the z-score is negative 1.13 right there. I think someone asked about another one via email. Let me see if we haven't done it yet, because there's a few we haven't done right here. I think we did the philanthropic. I don't think we've done nearsightedness of children yet. We haven't done, we'll do this one real quick, and then Ella will do your next one, and then I think we might do a little 320. So let's do the nearsighted children problem and figure this one out. So this one's very similar again. We're going to use the same equations. We have 14% of children are nearsighted, and we're going to take a sample of 150. This one actually uses the conditions right here, so we get to do a little review of conditions. That classic 10% condition where we need to sample less than 10% of the population. Here we are. Let's mark our notation. It doesn't give us a p-hat, but we have right here, there are 150 children. 14% are nearsighted out of all children like that exist ever. And that would be p, and this would be right here n, which would be the sample size. So we have here, we sampled 150 with a truth that 14% are nearsighted. So we can actually go and take mu p-hat, which is what we expect to see in a sample, mu expect in a sample proportion, and that is equal to p, and p is equal to 14%. We can also go here and get q. As soon as we have p, q is going to be equal to 1 minus p, so make sure whenever you have p and q that these add up to 1. So that's an important thing to look at, that p and q add up to 1. You've done it properly if p and q add up to 1. So we know p, we know q. My q looks like an a, so let's make it look more like a q. So there's p, there's q. So now that we have p and q, we can go here and find the standard deviation. The standard deviation of p hat is equal to p times q over n square root. And that's going to be equal to 0.14 times 0.86 over 150 square root. So what's up? Hey, we can do that. You bet, Roderick. We're going to do that here. We got one more question for 201 after this, and then let's head over to some 320. So stay tuned. Do not leave. Or if you do leave, come back. So 0.082. So 28. There we go right there. Oh, it's behind my head. There we go. So we've got everything written out right here. We've got our equation. We've got our standard deviation. And what we're going to do now is we're going to take this, copy it, and go over to Mr. David M. Lane's website and put in 0.14 there. And now we've got our curve. Now, what do the conditions actually mean? The conditions tell us if we can actually make this curve. The conditions are, should we be making this curve? That's the whole point of checking the conditions. And we have that we randomly select the observations. So did we randomly select these observations? Maybe. I don't know. It's maybe safe to assume. I wish the problem said it was, that they were randomly selected. So we need to randomly select these observations. And also, awesome, be right back. And we have here that they need to be less than 10% of all observations. And we have that there needs to be at least 10 successes and at least 10 failures. So what does that mean for this? 150, which is n times p, that's how many successes we expect, and then 150 times q, which is the complement of p. So that's how many successes we expect and how many failures we expect. So we assume these children are typical and satisfies randomization, and yeah, we seem to be good. What does the sampling distribution look like? Well, we just drew it out, and this is 3 standard deviations here. 14 was at the center, and we'd look at the bottom of the curve, just so we can see on ours, that 0.55, it is slightly different, but I don't know why. They're rounding it differently. Now, this is where people usually get stuck, but I want you to look at this. 0.56, that's 5.6%. So that's the lower end of 150 children, saying that on this low end right here, which is the curve we selected, we would expect about 5.6% as the lowest end of possibilities. So if we take that number right here and multiply it by this, we get 8.4, and that's this number here. Same thing would happen if you take the top number there of 0.224 and multiply it by 150, you'll get 33.6, which is the top number right here, and we should have everything correct. Yes. I really like the math chapters. Whenever it's math, I'm like, we got this. We can't go wrong on the math chapters. I think we did this one. We did this one already. So check out the other videos. I think we've done these. How do we get C? Which one? Part C? For part C, right here, use the proper curve. So for part C, use the proper curve by the mean and the standard deviation. So anytime I'm presented with this information right here, I always get, wrong slide. I always get the mean and the standard deviation. So make sure to solve for your mean of the curve. And here's the mean. And make sure to solve for the standard deviation. And the standard deviation is going to be how many units we're going up and down. And if you look at these numbers right here on the end of it, those are going to be 3 standard deviations away. And if you go back here to the problem, you'll see the same numbers down here, 3 standard deviations apart. So they're showing you only 3 standard deviations right here. Does that make sense, Cooper? Great question, Cooper. Let's throw some 50 points out. Tons of points. And then let's do the question Ella had. Or was it... And then Ella, did you have another one? Ella, did you have one more? Let me know. My brain's breaking. Could we do the randomly selected plays they need to contact? Yep. There we go, right there up top. So let's go grab... You're welcome, Cooper. Thank you for being here, Cooper, and working on this. Lots of practice. It's start early. If you get stuck, ask questions. The homeworks are going to be fewer and far between. I can't speak today. But I'd say they are more difficult. Like, the homework's going to be more difficult, but there's fewer of them, which is good. So, I mean, but they're harder. That's not good. So let's see here. Ellis said she wanted the randomly and select employees. Can we do the smoking section? Yeah, I think we can. Yeah. We'll go back here, Avery, and do that here in a second. Can we do the chapter 3 homework part? Is the probability that over blank % of these clients will make timely payments? Yeah, I think so. Yep. We're working away here. We got this. I think we're going to do Ella's question, then we'll do this. Here, let's see. Where is... Which one is it? Ella, how many randomly selected employees? Is it this one right here, Ella? Which, can you say the start of it? It was the last, did you see the number on it? I'm guessing it's around this area. Just in case, my question on task 2 is how to show each part of task 2, then what are we supposed to explain? Let me take a look at that really quick here. So 320, because we haven't talked to any 320 yet. 2 seconds. So many tabs open. Let me go. Let's see. Okay, that's the 1 hour warning. If you see which question it was. Okay. And here we go. Okay. There we go. And task 2, let me answer Roderick's question real quick, then I'll hop back to 201. So I agree with Parker. What would Parker say? I think Parker wants to start one. Yeah, we'll definitely do that. How to show each part of task 2, and then what are we supposed to explain? So for task 2, let's hop here to task 2. So task 2 description. Okay. So we have to have both simple linear models created. Then we're going to find both transformations. And then both multiple models created. Okay, good. And so the multiple models we are creating, next transform the X variables and create a multiple model with both transformed variables. Finally, check the conditions for the multiple models and conditions. So when you do this right here, you're going to make 2 simple linear models. So, and then task 4, yeah, let's do it real quick here, Ryan, because we've done a lot of 2-1. We'll come right back to 2-1, I promise. And we're going to go over officers. Don't worry, everybody. We're going to keep going. And thank you so much, everybody, for showing up. And let's do this. So with this right here, you need to create 2 simple linear models, search for transformations through those models. So you can use either find transformations or choose order. Then you're going to create your transform variables, and you're going to put those into the multiple models. So you need to make a multiple model with the transform variables, and then you're going to check the conditions for your models. Check all conditions for model, which is what you're going to do for the multiple model. So the whole point of this task right here, the big point of this task, is to create a multiple model and then check the conditions for the multiple model. Task 4 is where you're going to start analyzing the models. So this goes to Ryan's question right now. Task 4 is where you're actually going to do model comparison. So you have 3 models right here. So lastly, it's very important to compare and choose the best model. Compare your 3 models on 2 metrics. So let's just give some straight hints right here. I want to make this clear. R squared adjusted. So R squared adjusted and RMSE. Both of these metrics right here, so this is a huge hint, Ryan. This is like, we're dropping some major hints right now. The R squared adjusted is adjusted in the multiple world for how many variables are in the model. And the RMSE, the root mean square error, is the typical miss the model makes when predicting the Y variable. And this is adjusted in the multiple world. So what do I mean by adjusted? Multiple models get penalized on these. Both the R squared adjusted and the RMSE are penalized. The R squared adjusted is very directly penalized, but the RMSE will not always go down in the multiple world, as in you can't just throw more variables in and get a better model. It'll account that you're like helping it out by putting more variables in. So RMSE is a fair assessment in the multiple world. So we like RMSE because it in the multiple world, you're not just going to get better RMSEs by making bigger and bigger models. So these are fair assessments right here that we can compare models on in the multiple world. We can use the multiple regression. It's highly suggested to create a table. Check out earlier this week for making the table. I go through some really great steps of making a table. You can always just make a table in Word. I want to make that very clear that you can always just hop into Microsoft Word, make a table, and there you go. Next, select your best model and supply your variance inflation factor. So variance inflation factor is the code VIF, and you put your model inside there. We will go over this in class, but variance inflation factor is a bad thing. Variance inflation factor, and this actually goes to 201, big questions right here. If you're in class today, which today is the evening class, if you're in class today, we will go over VIF today. If yesterday we went over VIF, today we'll talk about VIF. So variance inflation factor is actually standard error squared inflation factor. And you know what's so interesting? This is the perfect cross back over to 201, the perfect crossover. We do not want variance inflation factor. And I'm going to show this, and we'll do a little 201, 320 right here, because we actually today started off with this. Variance inflation factor, so 201, check this out. Variance inflation factor. What the heck is variance inflation factor? Well, variance inflation factor, I often call it standard error squared inflation factor. And this is the factor by which we might be increasing the standard errors or variance. 201 has already seen this because this right here is the standard error of p hat. So what happens to our confidence intervals if our standard error is inflated? So whatever model has the highest R-square adjusted when we make the chart is the model. I would use your best model. Great question there, Seth. I would use the model you select as your best model to investigate the VIS. I think that's the one, but it wouldn't just be the highest R-squared adjusted. Look at it holistically because you've got R-squared adjusted, RMSE, and you've got the conditions. I'd also throw in some conditions there. Great question, Seth. And so what's going to happen to our confidence intervals if our standard error is inflated? If our standard error is inflated, and this is really important, this is a 201, 320 crossover right here. If our standard error is inflated, what happens to our confidence intervals? If you're increasing your standard error, which is your uncertainty, as we know in 320, if you're increasing your standard error, what happens to your confidence intervals by having a larger standard error, which occurs due to variance inflation, which is standard error squared inflation, because variance is mathematically standard error squared. So what happens to your confidence intervals when we have more standard error? So if the standard error increases, the confidence interval will do what? And just look at it. So 201, hopefully, like if you just look at that part of it, if the standard error increases, and that's something 201 should know. We don't usually talk about increasing the standard error in 201. We talk about changing the percent confidence or the standard errors relative to sample size. Yes, Seth, let's throw out some 100 points. Seth, a wider range, a wider interval. Now, when you're making confidence intervals for estimates in a model, like if we look at a model right here, I don't have any statistical models on the screen. We make one really quickly in Jump. So let's go over here to Jump, make a really quick statistical model. If we were to go over here to Jump, and we were to predict something like age from high school GPA, and we have here, ooh, that's a ridiculous model. If we go right here and we have a larger standard error, if you have a larger standard error, what happens to your confidence intervals? With a larger standard error, what happens to your confidence intervals? Well, you already said it, wider. And then if the confidence intervals are wider, then what happens? We would have a less significant interval because it could be more likely to include 0. So the wider the interval, I think it's better if I show it visually here. If you make an interval and you are trying to estimate the truth for a coefficient, you do not want 0 to be in that interval because you'd have the naive model. The naive model is a slope of 0. So if you have an interval and 0's down here and your interval gets wider, well, then your interval might contain 0. And the increase to the standard error is what can do this, because we'd be more uncertain, and the wider our interval, the more likely it is to contain 0. And if it contains 0, it's not statistically significant for estimates in coefficients. Does that make sense? And Ella and Seth, great job right there. Is this somewhat making sense? This is a more advanced topic. It's a 320 topic, talking about multicollinearity and variance inflation factor and the impact of confidence intervals. So there's a lot of crossover between 320 and 201, and we get into some more of the mathematical theory behind it. We don't actually have to solve mathematical theory, but we do need to understand that variance inflation is a bad thing, which is we can see the multicollinearity of the model, which is the overlap between multiple x's and how they explain each other. Does that help out? I hope, and we've gave some very direct hints on what to compare for here. Very, very direct. Yep. Next, select your best model and supply the variance inflation. Yep. So, Seth, you were right. Select your best model right here and check the variance inflation of that model. Show mathematically if the variance inflation factors are high or not. To see if variance inflation factor is high, we have to check the following. Another big hint. We'll mention this in class today. 1 over 1 minus r squared of the model. And this is our cutoff right here. So let's highlight this. This is our cutoff for high VIF. It's in the notes. I will mention it. I'll drop some hints during class. But this is the cutoff, Seth, and everyone else. That is the cutoff for high VIF. So probably this model over here is going to have a very low cutoff for high VIF because it's a very bad model. So this model right here has an r squared of that. So we take 1 minus r squared. And the high cutoff for this model would be 1 over that. And the high cutoff is 1.1 about. Very, very low cutoff for high VIF. But usually models that have a lot of overlap between the x variables will have higher cutoffs. So hopefully 320, how does that sound? Is it making more sense? 320, if you have additional questions, let me know, and then we're going to do some more. 201. We'll hop back in here. I think Parker had a question along with someone else. Can we do the chapter 13? What is the probability that over blank % of these clients will not make time of the payments? The bank payment, I think. We can do the bank payment. You got it. And I think 320, if you have any questions, let me know. I always try to evenly do it. 201 has a big assignment due tonight. 320 has assignment due tomorrow. Everyone's got assignments due. I got to stop putting out assignments. That would be such a good idea, right? Are there any votes for Brian should stop giving assignments? We'll give no more assignments. And then for a given confidence interval, having the margin of error requires the sample size twice as... Good help, Nico. Awesome. I can do that one right there. We can go back and do that. Let's go find the banks and timely payments. Let's go get the banks and timely payments. So here we are, getting the banks and timely payments. And here we are. So we have the banks and the timely payments, and this is your chance. So I think, yes, awesome. Let's do this. Oh, that would be false, Ella. So Ella, thank you so much. Ella, you're here. I wanted to just yeah. So I'll just throw the answer out. That is false. It requires 4 times, technically. It requires 4 times the sample size to have the margin of error. So just throwing that one out there for you. So what are the mean and standard deviation for this problem? Let's go right here. And I can show that mathematically after this problem. Let me show it really super quickly. The mathematics behind that is P times Q over N square root. And if we want to get half of this, we have to do the following, which is going to turn that into this right here. So you have to take 4 times to get half of it. So I do it in other videos too, so check that out. Let's take a look at this problem right here. And here is the problem. Have you done the restaurant investment website one? I don't think we've done that one today, Iris. Let's do that one next here. You got it. Keep adding questions. We're going to do as many as we can. And I need your help to identify the notation in this problem. Everyone, practice along here. What do we have? The more help we get, the better we do. So I'm going to write the notation right here. These are equations that are in the chapter. We know that we're going to be searching for these. It's right there. And I need to know the notation and what we have. You are right. Nice job, Leslie, right there. Great job. That is N. This is going to be P because that's the truth. And since we now know P, we can get Q equals 0.94. How do we get that? These are complements. Always remember P and Q are complements. P hat and Q hat. Can you show the double standard deviation formula again? It'll be 4 times, Avery. I can do that one next if you like. We can go over that one here. And great job, Avery. It's 4 times since we are doubling, or not, we are not doubling it. We're taking half of it. You have to quadruple your sample size to get half the standard deviation. And I have some videos going over that yesterday, but I can do that one next if people vote for it. So we're just going to say, if everyone's like, do this question, we got this. So here we are. And so the answer is take 4 times it. I'll throw out some quick answers today on that one. And so we have the equation right here. You bet. Let's do that one next. And let's put in the numbers. And so now we got to go right here. That's a really low percent. It usually doesn't do that low. And we're going to put in the numbers. We have now found the standard deviation. So let's find it. I got a high cutoff of, yeah, that seems about right. You must have do you have a really good model? Is your model, what was the R squared of your model, Seth? If you tell me the R squared of your original model, your R squared of your original model must be something like 98% or something like that. No, wait, 98? No, 96%. Did you get an R squared of 96? Non-smoking? Yeah, let's do this. P times Q over N square root. You must have a 96% R squared, which, are people getting that high? Yeah, 96% or so, yeah. That's, really? Send me your model set. That's pretty awesome. That's great job. I didn't think the models would go that high. Yeah, send me that. I want to see that. That seems really high. I'm impressed. I'm like, wait, the model's that high? So we have here the mean and the standard deviation. Let's go put our mean and standard deviation in here. This is the David M. Lane website. And there's the David M. Lane website in the chat. There's the mean, there's the standard deviation. And what are we looking for? Now, they always have us check the conditions because to draw this curve for the data to be normal, you have to meet the conditions. So you have to meet the conditions for the curve to be normal. If you do not meet the conditions, then the curve will not be normal. So why do we meet the conditions of randomly select the observations? The observations are less than 10%, and we have at least 10 successes, at least 10 failures, which would be found via N, P, and N, Q. That's how many successes and failures we expect, and they're both greater than 10. We meet the conditions with reasonable assumptions, and we have here the mean of the distribution. And let's go grab P times Q over N square root. Double check our work and delete down. 3 decimal places. Does that round up? Seriously? I'm going to check this also because I think everything should work properly. This is where usually people get stuck, but let's take our famous guesses at it. We have here 9%, which is a little bit below 2 standard deviations. There's 2.5% of the area above here. So if this was a multiple choice test question with A, B, C, and D, which of these do you think would be the right answer? Do you think it'd be 1%? Do you think it'd be 3%? Do you think it'd be 18%? Or do you think it'd be 20%? What would be the answer right here? Just, yeah, thank you so much, Seth. I'll check that out here in a little bit. What do you think would be the answer for the area that would be above 9%? What would be the area above 9%? There's probably 2 answers you're between right now. You might be between 1 and 3%, but we know this has to be more than 2.5%. So, yep, We know it has to be more than 2.5 because 2.5 is the area above here. So it has to be more than 2.5. And that's kind of how we do multiple choice questions. We might not give you the drawing though. Yep. So B is the most plausible answer. This is just a guess right here. Just want to state that time and time again. Who needs David M. Lane when you can just guess the answer? Let's do that. Let's go. We got this. Here we are. Let's put the actual answer in. We're going to go above 0.09, and we're close enough. 0.037. So this is the David M. Lane getting the exact answer right here. And yeah, there we go. So 3% was close enough, or however many decimals I entered in. This was close enough right here. And it's got a range. Oh, I bet I was right on the edge of that range. Oh, no, it's really nice. Wow, that's super nice. No, why do I ever miss this? Holy mackerel, that's nice. Okay, now it finally is wrong. It's got a really nice range in here. Wow, it's very, very forgiving on the plus or minus. I guess because of how you could round this. I could have just said 4% and it would have given it to me. So once again, the real answer is right here, shown by putting in the standard deviation. If we had rounded the standard deviation, we'd get that right there, which rounds to 0.039. If a p-value is NA, would you say that it has failed the assumptions? So if it's NA, it's just missing. Great question right there, HDT. You should look at the plots. If the p-value is NA, just be like, well, I guess we got to look at the plots for this one because I don't know. So you would say that that test could not be performed. Editors, paper, you bet. Which one? Editors preparing. Tell me if you see it, Ella. Great question right there. So I would look at the plots, HDT, and I would mention that the test could not be performed. So you're welcome, Parker. Great job right there. So editors preparing. Tell me if you see it. We did school budget. A new restaurant. People want that one too. It's in the other set, right, Ella? It's part 2? Yep. That's what I was thinking. And then we'll come back and remind me to do the... Did we do the school budget one today? You ever have where things just blur together? Did I do the school budget one last semester? Oh, we did it. We did it. Look at this. We got instantaneous right here. We are just like total. We got this. We got this. We got this. And let's go right here. And there we go. Already, I'm losing my mind. Let's go back here. There we go. There we go. And restaurant one, you got it. Let's do restaurant one next here. And then nearsighted, you bet. We got enough time. Let's do this. So editors preparing a report on the economy are trying to estimate the percent of businesses that plan to hire additional employees in the next 60 days. They're willing to accept a margin of error of 4%. Okay. This is a math problem. I don't like math. And they want a confidence of 95%. And so then they want to figure out the sample size. So they want to figure out this. So we know mathematically, this is from the chapter right here, around 26 minutes. Oh, I did it? Oh, wait. Are you helping out? Awesome. Thank you so much. Thank you so much, everyone, for helping out right there. Iris, Iris, 50 points. Thank you, Iris. If you're telling, because I cannot remember which one's done. So I'm like, I do not remember. So let's go right here and do margin of error is equal to, if you're wondering what I'm about to write right here, I'm using this formula, which is in your notes. You don't have to memorize these things. They are given to you for the test, but I'm using this formula right here, and the margin of error is the part after the plus or minus. So the part after the plus or minus is the margin of error. So I'm just going to use this right here, the z-score. It has a star because we can pick it based on the percent confidence. And I'm going to use this right here. Now, we want to solve for n. We want to solve for the sample size. Have we done it? Everyone remind us here. I can't remember. I cannot remember. That's a really good question. Yeah, check regression is very redundant. Check regression is very redundant. Let's go ahead. Great question right there, HT. It really is. It's like, well, we got this. So we're going to solve for n right here, and we're going to make our lives easier. This makes our lives way easier if we solve for the sample size. So what we need to do now is we know most of this information right here. Ooh, this one's such a tricky one, and I'll tell you why. They do not give you p. If they do not give you p hat, you would have to assume, this is a huge assumption, and you would thus assume q hat is equal to 0.50. And I guess technically, it might be easier if we just solve it out, but let's solve this mathematically and solve for n. Here we go. So we're going to solve for n. The first thing I'm going to do is I'm going to take the margin of error. I'm going to divide it by z and z star. And we get over here square root of p hat q hat over n. The reason someone might be wondering, why did we solve for 0.5, or why did we say it's 0.5? Without any other information, we're just going to put it to the middle ground of like, well, I don't know what it is, so let's just guess 50% because that's in the middle. There's no other, we don't have a good estimate, so we're just going to use 0.5 because that's average. So yeah, that's the super confusing part of it. That I think that isn't one reason this question can be difficult, because you don't have p hat, so you're like, well, what's p hat? It's like, well, I don't know, 0.5. Let's just take a guess. You wouldn't just take a guess like 0.9 or something like that. 0.5 is the absolute middle. It's it's like, well, you don't want to go to this side or this side, so just go to the middle, 0.5. It's the safest guess. And so now we're going to square both sides. What we're trying to do right now is we're trying to solve for n. We're just trying to get n isolated by itself. This will have p hat q hat over n. And then we're going to take, and what I like to do now is I like to flip them. So you can literally just take equations and flip them like this. I mean, that doesn't look good. So we're just going to flip them by going here and going z over me is equal to, square this right here. So we're just flipping them, because you can literally just flip things like this. And now we're going to get here that n, this is finally on top, p hat, q hat. And this is where life gets easy, because now we're just going to multiply both sides, and we're going to get the p hat, q hat on the other side. We're just going to take here and go p hat, q hat, and then z and me, margin of error, squared equals the sample size. So now all we do is we plug in our information. Remember, p hat and q hat are 0.5. So here, I'll write it out right here. So this is the solve now. We have 0.5 times 0.5. And then z is 1.96. I'll show that here in a second. And I think they want a 4% margin of error. And then this has to be squared. So all of this right here, I'll vanish for a moment. This right here is the solve of everything. This is the full equation solve. So we'll just put that right here. That is solving for n right there. And why do I have 1.96? Because we have a 95% confidence interval. And let's bring up the David M. Lane. Mr. David M. Lane, he's in the chat. And 95% confidence interval is a z-score of 1.96. And there is the 1.96 95% confidence. And that is why we choose this z-score right here, because that's relative to the percent confidence, which is 95% for this problem. And once again, just to show it, this can be found via the David M. Lane website. I'll drop it in the chat here again if you ever have to change it to like a 98 or a larger or smaller confidence interval. So if you had to go to 98, there's the z-score right here for a 98% confidence interval. So we're just going to take and going to solve the problems. We're going to cross our fingers to make sure we did everything correctly. Always make sure. There we go. And actually, you know what I'm going to do? I'm going to do the 1.96 divided by 0.04. And then we're going to square this. So there's the square. And then we're going to times that by 0.025, which that is. So that's 150.06. Be very careful. Some of these say round up. So make sure to round up. If you don't round up, please email me. Don't worry, I'll give you the points back. Oh my gosh. What have we done? I knew we'd have an error. What did we do today? What did we do, Ella? This was our one error. What did we do? Let's look at our mathematics here. Well, that's no fun. I was so excited. I was like, we did it. Have you done the question 13 about the investment website? I don't know if we've done that one yet here. So let's check our mathematics. They want a margin of error of 0.04. There's the margin of error. Maybe we should go up here and solve it this way. Everything looks accurate, and I've done this one a bunch of times. 0.05 times 0.05. Let's see. That's 0.25. 1.96 divided by 0.04 square. Oh my, there had to have been 601. What happened here? Did anyone see it? Ella, what happened? Because I'm not even joking. Like, if you notice, I did not change anything. Like, rewind the tape on this. Rewind the tape on this. Because 1.96 divided by 0.04. There's that. Square it. Times. You know what I must have done? What am I doing? 1.96 divided by 0.04. Most things happen as calculator errors. And then times by 0.25. I did it twice. I multiplied by 0.25 twice. I don't even know how I did that. But I multiplied it by that twice, and that's where we got the error. I was like, this doesn't make sense. This is mathematically accurate. Everything here is correct. It was just user error. I did this procedure right here twice. So I accidentally multiplied by 0.25 because that turns out to be 0.25. I multiplied by that twice, and that created the wrong answer. So yes, we did everything correctly. Oh, I didn't clear out the 0.25. Yep. Thank you so much, Ella. 50 points right there. I was like, this doesn't make sense. This is mathematically accurate. I was like, I've done everything correctly. I do not understand what I've done wrong. So yeah, there we go. Good stuff right there. Got the question right. Watch out for those user errors. It's usually just a mistake we make while entering it in. Make sure to round up when you get the answer. You need to times that by 4. So make sure to round up. User error happens to even me. It happens sadly. Put on some music here. Which questions have we not done today? Which ones have we not done? So if someone can say, Brian, you have not done this question, we're going to put that in this video today. I need your help here, everybody. Which question have we not done today? I'm going to pull up the chapter 13, part 1. And if you can identify a question we have not done today, we're going to do that question. Which question have we not done? We did the nearsightedness of children. We did that one today. I remember that. We didn't do this one today. That one's a quicker one. I feel like we did the school budget. We did the school budget one. I do remember that today. I think someone just posted in the chat. The restaurant one. Yeah, we did not do the restaurant one. Let's do the restaurant one. You are correct. Let's do the restaurant. Here we go. Okay. And then we can do investment website. I think we got enough time. You got it. Let's do investment website and restaurant. So good to see you here. Let's get both done. Let's go. We got this, everybody. Let's do this. We'll put on, we're going to put on chill music. Let's do this. It's not chill enough. For fixed margin of error, large sample size provide greater confidence. That sounds false because larger sample size will not impact confidence. Oh, good. Let's do this. Yeah, I think I did this one on a past live. I think Ella might have asked about it. It might be very early. I want to say this. Do start on these things early. Do not worry. If you're starting this, you are doing the right thing right now by being here. If you wait till tonight to start these, someone's watching this right now at 11:59, and they're like, oh my gosh, oh no. If you wait till tonight, it's a lot tougher. So do not wait till tonight. Start these early. Swing by office hours. Thank you, everyone, for being here. Thank you so much. I'm just going to throw out another 50 points. We're going to do this problem right here. We're going to get both done. You are doing the right thing by being here right now. I know life is busy. Starting even right now. Great job. Let's do this. So a new restaurant has 132 seats planned. 132 seats. That's going to be the sample size. Always identify your notation as you go through the problem. Next, we see studies show. So, oh, you're welcome, Paige. We're just here for positivity. I don't want anyone to feel bad. If you're watching this later tonight, like you're watching this and you're hearing this, just swing by anytime. Swing by anytime. Put a message in the comments. Say, hey, Brian, can you explain this? We're just here to help. And I'm always talking to past Brian, because past Brian would be watching this at 11:59. Don't worry. I'm not mad at Past Brian. I just want to give him some advice. I want to say, look, just start early. You got this. Start early, and then you can ask all the questions. So this is the mean and the standard deviation, P times Q over N square root. And so we need to know what Q is. Everyone in the chat, we know what Q is, right? Don't worry, it's a common question. Everyone says, wait, how do we find Q? So we know what P is. Q is going to be 1 minus P. Like, Brian, I know that so quickly, but someone didn't know it. Now we know it. Avery, great job, Avery. Excellent work. So we see here that Q, whenever we find Q, what we're going to do is we're going to look at P and Q, and we're going to say, are those complements? And we look at this, and we say, yep, that's a complement. These two right here add up to 1. We do it as a percentage, they do. So now we need to go ahead and start solving these. We would expect that 55% of our restaurant would want non-smoking. Smoke-free, yep. Now we need to solve these numbers right here. We're just going to plug in P times Q over N square root. P times Q over N square root. Let me zoom out. P times Q over N square root. We do need to meet the conditions, but we would meet the conditions for these. Really? Really? There we go. And let's go ahead and solve this. P times Q over N. Don't make mathematical errors. Check out the last problem. Square root. 0.0433. Now, this is a common error on this problem. So now we have the standard deviation right here, and we have the mean. So what I'm going to do is I'm going to take these answers, I'm going to drop them into the David M. Lane applet. David M. Lane applet, let's show it on the page right here. I don't get why you wouldn't just do 0.55 times. Oh, so great question right there, Paige. So Paige, I'm giving points. So I'll send that. I'll fix that, Ella. Send that to me. Since I didn't have time to address it, Ella, send it to me. If that was the only thing you missed, I'll fix it. So I feel bad because I kind of was like, I don't know if I knew the question fully. So yeah, I should have looked at it fully. And I'm sorry about that, saying the wrong way on that one. That would be how many we would expect, Paige, right there. But we want to look at how many we expect. Let's go here to this. And then go how many standard deviations above it. And I wish it would show it. But we want to look at how many we'd expect and then go how many standard deviations above it. So this is how many we expect. It is true that we expect 55%. So we'd expect, we could look at this right here. Let's copy that. And we would expect out of the 132 seats to need this many. We'd expect that on average. But maybe some days we have a little bit more because our restaurant might fill up. So we'd expect maybe about as high as this because every day the restaurant fills up, we're going to need a certain amount of seats reserved for non-smoking. And so with a certain amount of seats reserved for non-smoking, we could need as much as this or as little as this. So we want to go to the mean plus 3 standard deviations. And that's what the question gets at right here is we want to go to the mean plus 3 standard deviations. To be very sure, exactly. Because think about this. Like, yeah, you probably need about 72 seats. But sometimes you'll need a little bit more than that. Sometimes you'll need a little bit less than that. Every time you take a sample, like every time, which is when the restaurant fills up, every time the restaurant fills up with a different group of 132 customers, it's going to be somewhere in this range probably. And this is where we'd be very sure that we have enough non-smoking. This is back in the day when you could smoke in a restaurant. Not like Brian smoked in a restaurant, but I did work in restaurants where you could smoke. Cheddar's, Kingsport, Tennessee. So 68% is apparently 3 standard deviations up. Let's check this by going to the mean plus 1 standard deviation plus 2 standard deviations plus 3 standard deviations. It is almost exactly 68%. So actually what you've done right there, Paige, you've already shown the mathematics. We're just going to take this number right here and just like you did, multiply it by 132. So this number right here is the proportion we would expect to need on a very, very extremely high day. That's a bit of an outlier right here. And that is what we need. Now, even if this was, I'm going to change the number slightly. Here's my number. Like, I'm going to pretend I got this. If this is my number to be very sure, as you're saying, I'm going to go over here. And when I enter it in, I want to note something. What is the answer right now? What is the answer? I'm pretending I got 89.2. I got like 89.7. But if I had gotten 89.2, what is the answer right now? Be very careful. Someone's already hit enter right now. I'm like, no. It's not. Sometimes it does that. Try deleting the decimals, or you might have to add them in visually. I know it's so weird. Like, I'll show that here in a second. So what would I enter in right now for this? I'm not going to enter in 89.2. 90. Great job, Paige. Because it says round up. It's weird. It says round up because we're just going to like be super, super sure. Sometimes David M. Lane doesn't show the 3 standard deviations. Delete down a decimal. So if it doesn't show the 3, just delete a decimal or 2. And then you can always check by going to the mean. And I think I still have it saved. And if you notice, I did this to double check. I added on, here's my standard deviation. So I'm going to go to the mean. I'm going to go to the mean plus 1, 2, 3 standard deviations. You can use the calculator that way. So you can do the mean plus 3 standard deviations. So you could take your standard deviation times it by 3 and add that to the mean. Does this make sense here, Iris? I'm mathematically finding where that position would be. So you can use your mean and standard deviation that we find and just do 3 standard deviations above the mean by taking this and multiplying it by 3. Oh, you're welcome. I appreciate it, Roderick. No worries. I like helping out. I just want to say thank you to everybody because some of these office hours are getting like 400 or 500 views. I would never expect. I was telling my fiance that I was like, yeah, some of the office hours get 400 or 500 views, and she's like, that's insane. And she'll try to put me in my place a lot of times, or like not in a bad way, but like I'll just be like, oh my god, the YouTube channel. She'll like, whatever. But she's like, no, that's really amazing that people are watching them to that extent and using them for help, and it really makes me feel good that people utilize this. That's what makes me feel good. The more, and so is it marketing research? We're multiplying by 3 because we want to go 3 standard. So right here, this part of it, great question, Avery. We're going 3 standard deviations up right here. Road to 2 mil. Yeah, exactly. 2 million views. So this right here says we want to be very sure. So we're going to go to the mean plus 3 standard deviations. And then we have one more to do today. Thank you for all the questions. Investment website. That's one, Bryce. And good to see you here, Bryce. We just got the 1 million views. We got to get to that 2 million views, right? Investment website. Where are you at? Look at this. We got this. You bet, Lizzie. We can do this. Here we are with the investment website. And once again, all you have to do to like help this channel out is just watch. Just watch the videos. Just come here, ask questions. That's all we need. Swing by, Charlie swings by, get some points, all the good stuff. An investment website can tell what devices are used to access their website. The site manager wonders whether they should enhance the facilities for trading via smartphones, so they want to estimate the proportion of users. Categorical question. They draw a random sample of 408 investors from their customers. Suppose that the true proportion of smartphone users is 27%. And yeah, what would they expect the distribution to look like? Now we have to randomly select observations. We have to select less than 10% of the sample, and we need to meet the success failure condition, and we do meet it with those right there. And what will the distribution now look like? I can go back to that Avery here in a second if you like. I think that might be what we have time for. If we meet the 3 conditions, now it's not listed on here. If we meet the 3 conditions, the distribution will look what? If we meet the 3 conditions, the distribution will look what? If we meet the 3 conditions, and to, like briefly, Avery, you want to go to this number right here. If you draw your curve, this is the proportion you're looking at right here, Avery. Does that make sense? If we meet the 3 conditions, and so put it into the David M. Lane for that one, it'll look normal. Andrew, good to see you here. Andrew is right. If we meet the 3 conditions, it'll look normal. So I do not see normal on here, but I see something related to the normal. So which of these sounds like the normal? A, B, C, or D? Exactly, Parker. And so which of these sounds like the normal right here? Which of these sounds like the normal? One of these, A, B, C, or D. You're exactly right. Unimodal and symmetric, that's classic normal right there. What would be the mean of the sampling distribution? Well, 0.27, because the mean for the distribution of the sampling distribution is mu, and let's go back, we have it in the notes here. Where do we put it? Was it here? There we go. So the mean for the distribution of the sampling proportion is equal to, I think they said 27%, right? Is equal to 27%, because that is equal to P. And then we need to find Q. So in this problem, actually, you know what? Let's just copy it because this is going to look really confusing if I do it that way. So we need to find the mean and the standard deviation. And they just want the mean and standard deviation. Good. So we need to do the mean and the standard deviation. Okay. And we will be back for later in the day office hours. So we will be back. Always highlight your notation. So that is P, and Q is going to be equal to 0.73. Remember, P and Q need to add up to 1. So make sure those two add up to 1 right there. Here is the sample size. The mean is mu P hat equals to P. The standard deviation of P hat is equal to P times Q over N square root. Hey, Mon, good to see you here. We did some 320 earlier. Check it out. We will be back later. So we're just going to take here and put in P times Q over N square root. So P, I always want to draw these out. I know people watch these later, so let's write it out. Got to slow down here. We'll do P first. So P times Q over N square root. That is what we were putting into the calculator. P times Q over N square root. Please tell me if I typed something wrong. And square root. That's the standard deviation. And this one up here is just P, and we know what P is. It's 27. So we've got both of these answers done. And we should be correct. We'll cross our fingers, as we always do, and say, not today, my Pearson. Not today. You got one on us. But today is not your day, my Pearson. Today is not your day. Of course not. Oh, you were stuck on this one, were you? Oh, that's so good. That's a really good question right there, HTT. The Milton Scholars do so many different things. Doctor, if I were to do this, Lizzie, that's awesome. Lizzie, congratulations. We'll head off here in a second. Yeah, awesome job, everybody. Like, great job. Amazing work. Man, I'm just putting on, like, let me find a good song right here. That one let's see, we need, like, better, like, congratulatory music. This one's so happy and just so chill. You got this, Paige. You got this, Paige. It's all right if you don't get 100. It's all right. Paige, we'll get some positivity in the chat right here. Give it a shot, Paige, if you want. If you feel you've gotten them all correct, or if you, like, I give this a good shot. Did we do it? And we will come back later. Got to get prepared for the next class. Got to make another cup of coffee. Woo! Oh, I'm here. I'm playing my happy song. Playing my favorite happy song here. This goes out to everybody. It's my favorite song on this pad right here. It's Coldplay by Josiah Wilkinson. It goes out to Paige and Iris and Lizzie and everyone making hundreds right there. If you didn't make 100, that's okay. Because we're going to practice. We're going to get this material down. Milton Scholars. Lots of opportunities there at the Milton Scholars. Basically, I know, Paige, great job right there. Amazing work. You're like, done for the day on this. Got it. Just need a review for the test. Make sure to review it. It's so easy to make an error. I made an error today. I know we have class. Right, Iris? I need to go make some coffee. Whenever I feel myself getting tired, I do this thing where I just, like, pull more energy. So if I'm feeling tired, I, like, try to, like, I just, like, pull that energy in, just because if I get tired, I know that everyone else is just falling asleep. So I try to pull the energy and make sure we get some energy. So I need to go get some coffee to make sure I have real energy, or, like, caffeinated energy. But I meant the answer. Yeah, so does that answer HCT? There's lots of different things that people in the department will be researching. If I were to do it, I'd probably want to work with Dr. Michel Ballings. I don't know if he's taking on Milton Scholars right now. But if you're talking about, like, the opportunities, it all depends on, like, what each professor is doing. And Dr. Michel Ballings, really awesome guy, and he does a lot of social media research. So a lot of cool stuff right there. Got to stretch? Yes. I've been doing Ring Fit on the Switch, which is a lot of fun. I'm only up to, like, level 2 on it. Or I'm at level 8, but, like, World 2. It's a lot of fun. It's actually pretty tiring. I'm like, holy crap. It's pretty tiring. But HCT, email me about this, and we will go into more detail. And reach out to Dr. Petrie. The more you reach out to people, it's just people know your name. They say, like, hey, good to meet you. And yeah, I'm always excited about people reaching out about Milton Scholars, because I really like when my students get Milton Scholars. I mean, I want everyone to get Milton Scholars, but I like hearing like, Brian, one of your students is a Milton Scholar. I'm like, yeah, one of mine. Taught them, and now they're doing amazing stuff. And one of our Milton Scholars, Nanika, she's kind of like Harvard. She just won another award, like a poet award or something. I saw it on LinkedIn. I was like, just I'm gonna hear about her being president in a moment. Like, I'll be like, she's just doing everything. She's amazing, like, great job. And I love hearing about the great things that our students are doing, because it makes me feel good. It's just like, I'm proud of them. And so I'd like to think I played a little bit of role in helping them, and they would be like, oh, Ryan, you helped so much. I'm like, no. Because they've said that to me. I'm like, no, I just teach you how to do data stuff. That's all I do. But I really like it. And that's probably one of the best things about teaching is hearing in the future, like, and I've got a lot of students who've gone on and graduated and hearing back from them. So Andrew, you better be emailing me when you graduate. So I want to hear back from everybody. I want to hear how things are going, and we're here to Vols help Vols. One thing I want to mention is one of the students who graduated reached out to me and he said, our company's looking to hire. And I said, thank you so much. So you'll hear more about these opportunities. If you're interested, I've already got, it's TVA with Tennessee. So, and if you have opportunities for students after you graduate, please tell me, because we're here to Vols help Vols. That's what we do. And Vol means all. With that, everybody, we'll be teaching here in 12 minutes. So get ready. 201, I'll see you soon. Bye for now, everyone. Bye. You got it, Nico. Apply. Great job. I don't mean you got it as in you'll get it. I just mean I want you to keep applying. I don't know what'll happen. I'm not in control of that. Bye.